Hello, this is Roger Terrell. I'm here. Eventually it will focus. There we go. Good. Hello, Hannah. How are you? Hmm. Hello, everybody. How are you? Good to see you all.
Hello.
Hello, hello. How are we doing? Let's see here.
Good afternoon, Dr. Terrell.
Hey, Vigo. How's it going, buddy?
Kind of tired, but other than that, pretty good.
Uh-huh. Well, we're going to see what we can do about that. Yeah. We're going to have some fun with science. I hope. And that may mean that I have to share with you all my my project that I'm working on. I think that may mean that. I've been working on making a temperature controller. I have a tube furnace, which is a quartz tube. It's 2 inches around, and it has this heating tape wrapped around it, and you can slide things in and flow gas through it and heat it up, you know. And we use it to coat things with copper and silver and gold, and sometimes a nickel and cobalt. We're trying to make all these different types of inks. And the trick is, don't tell anybody. The trick is to start with the metal carboxylates, like metal acetate. You know, like if you dissolved a metal in vinegar and you boiled off everything else and you just had like iron acetate or whatever, then you can take that and you can make you got to make an ink out of it. You got to add stuff and make a little fluid out of it, and you can spread it on a surface. Then you heat it up, and what happens is the acetate, it's like it's a light thing, right? It says, no, I don't like you, I want to fly away, right? And so it does, and then in so doing it leaves its electron with the metal, and you get a carboxylate radical that leaves, and then they decompose and do all kinds of stuff. But the trick is that you have a metal film left over, and so I've been working on a temperature controller. This is my cool box. I don't know if any of y'all can recognize, but it'll focus eventually. There's an Arduino little microcontroller in here. And then this is a solid state relay. And this is a little thingy that takes a thermocouple. I'll show you the thermocouple. Here's the thermocouple. That I've got that in a dealy bobber that I heat up here. Got it in a heating mantle along with some water. And I'm just programming this to control the temperature, right? So that I can ramp the temperature up and down. And it's really interesting because it sort of works, you know, it actually works. And that is just amazing for me. Let me see if I can show you I can share my thingamajiggy with you.
So this controls like the temperature around you?
It controls the temperature in this thing.
Oh, okay.
Right now it's like this thing. This is plugged into the temperature controller. And so it's the feedback is that it goes from the thermocouple to the controller, and then from the controller to the heater, you know, and that closes the loop there, you know. And then here's the code that I use. And so far, this is what it looks like. This is a lot of it is user interface, right? And I have to have a user interface that pukes out all this stuff. Like to control the temperature, you need these 3 parameters. You need here it basically it's all right here, right? This is an object. This is the Arduino sketch pad here, and you can define objects in C++. And I didn't make this one. I don't know how to do objects in C++. I just use them, you know. But here's how you do it. And you say my PID. PID is an object type that's in this include file. And I'm declaring an object called my PID, and it has an input. That's the temperature. Set point. Right? That's you say that's the temperature I want, right? Then there's the output. That's the temperature that it actually is. Oh no, shit. I'm sorry. I got that wrong. The output, that's the heater. That's the value that it's heating to. I forget what this is. Damn it. Oh my gosh. Set points, that's the temperature you want. Then you got these 3 parameters, Ki, Kp, Ki, and Kd. That's the proportional, integral, and differential parameters in this control loop. Input, output, input, output. Anyway, I forget what they are actually right now, but it's just my brain is a very rough sieve right now. But anyway, it seems to be working, and I'm really happy about that. I can get, this is where I get the messages in and out from the user, and this is where you this is where I measure the temperature. I measure it like 100 times, convert the voltage into uh, a real number. You know, I even have this. I even compute the confidence interval on the number. Oops. And then, oh, input is the temperature. And I'm not sure what output is. Oh, output must be the heater level. Input is the temperature, output is the heater level. Then there's the set point temperature, which is the temperature you actually want it to be. Yeah. Anyway, I'm having fun with that. And I figure since you guys are a little bit bored and a little bit oh, thank you, Audrey. I appreciate that. And maybe a little bit tired, we could share that a little bit, but it keeps me off the streets, keeps me out of trouble. My students are doing the fun work. But and I'll give you an update on that next time. But what I would like,
program.
what?
How long did it take to program?
Oh, this this is never done in one sitting. This is always like probably 10 cups of coffee and like 5 or 6 or 7 sittings, maybe an hour each, and I'm not fast or anything, and other people can just rip this shit out, but I revisit it like 3 or 4 times a year, and so I forget a whole bunch, and it's like even the basic syntax I have to go back and say, what's a double, what's a float, what's the basic data types and everything. I'm always just looking at the website trying to figure it all out. But once you kind of get it, it's really fun. Once you kind of get the programming piece, it can be real addictive. And I really wish I could get my son into this, but he's so far he's kind of resistant. And I think I screwed him up basically. I think I overly praised him too much when he was little. And they say that messes up your kids. Did any of you get overly praised when you were little?
No.
No, I didn't think so. You're always like, so how many of you have parents that are always like, no way, says. How many of you have parents who praise the process? They say, oh, that's a nice drawing, right? Not like, oh, that you're such a great artist,
That's probably more in line with
Yeah, I know that's how you make healthy children. That's not what my poor kid has had to deal with, because I'm so insecure. Your parents would throw away the drawing and your art is trash. Oh, John. Oh, God. Oh, geez. Well, maybe that's what's good for us. I don't even know. I'm beginning to think it's like I'm always like trying to be my child's friend, but I've heard people say, never do that, never ever, you're not your child's friend. Don't do that, right? But it's like, he's my only goddamn friend. How can you say that? I need him. I need this child. But anyway, he also has ADHD really bad. Can you imagine where he got that? Look, a squirrel. So anyway, he got that from me and his mother and all of our relatives. So kid's got a lot to overcome. But anyway, I wanted to share about, let's do the Pound-Rebka experiment here. Let's go up. So if you'll recall from last time, we were talking about absorption spectroscopy, And it got a little complex, right? Oops, come on. There we go. We started kind of here. There we go. I don't know, that helps a little tiny bit, but we're talking about this kind of weird absorption thing, which uses gamma rays, right? And the reason that I like to teach it to y'all is that it's weird, you know, but it's all completely general about it's all completely general about absorption spectroscopy, which is what everybody does, you know. And the first thing you have to remember is that when this is an energy level diagram where you got, these are different states, right? There's 57, cobalt 57, right? Which undergoes an electron capture, and that lowers the energy of the system. And this is an excited state, iron 57. And that iron 57 can then decay versus in one of two ways, right? It can go all the way down to the ground state and emit this gamma ray, or it can go down to a metastable site emitting this gamma ray. And this metastable site hangs around for a couple nanoseconds. And then this guy emits a gamma ray, this 14.4 keV state of iron 57, right? And the difference between this level and this level, right, is a gamma ray that this same nucleus can absorb, right? So this gamma ray comes from a fairly long-lived iron 57, and when it's emitted, this gamma ray can go flying off into space and find another iron 57, which will then absorb it. Right? So if you're a detector off here to the right, and we just have the source and no absorber, you count gamma rays, right? 1, 2, 3, 4, 5, like that, right? But if we then put an iron 57 in the way, do you detect more or less gamma rays there? Just answer me that, just real simply right now.
Can you repeat the question, please?
If you put the absorber in place, if you put this absorber in place, do you count more or less gamma rays on this detector over here?
Less?
I cannot believe it, Vigo. Raymond, can you believe Vigo?
Honestly, I can't believe myself sometimes.
Celine, what do you think?
I don't really know.
Okay, all right. Let me see. How about Jerry? Do you know? This guy's emitting. You're detecting them here. And then you introduce an absorber in the path between the source and the detector. Does the count rate go up or down?
I'm not sure.
Okay. Lucas, do you know?
Last lecture, did you say that the absorber would get excited by the X-ray and then emit X-rays? Or no?
Ah, yes. This absorber will absorb these gamma rays. It'll come up here, then it'll drop back down and it'll emit gamma rays. That's true. But the gamma rays that it emit will be isotropic. They'll go in every direction.
So we're only counting X-rays or gamma rays?
These are all gamma rays.
Ah, okay. Well, it would probably be less than.
So why do you think it would be less than?
Well, because they're absorbing some of the gamma rays and then also they're emitting some, but you said it's isotropic, so they're going in different directions.
Right.
And not all of them will be absorbed by the detector.
Exactamundo. Exactamundo. What do you think, Sadana?
Makes sense.
Yeah, that's a good answer. I like it. I'm sorry, Vigo. I made fun of you earlier.
Oh no, it's fine. It's fine.
I just didn't want to just say, oh yeah, you're right, and then move on, right? Because obviously it's like this is like the basic premise of the entire experiment, and you've got to get it, and then everything else falls into place, right?
Mm-hmm.
So I can't just gloss it over. So, essence. What do you think about this experiment so far? Have a source emitting gamma rays in all directions, right? Then off to the right, you have an absorber, which absorbs gamma rays. Then you have a detector. If you remove the absorber, will the count rate go up or down?
I don't really know.
Ah! Okay, who can explain it to essence?
I can explain.
All right.
Okay, so basically from my understanding, when it's coming from the source and you put the absorber in the middle, essentially what happens is the gamma ray is going to excite the absorber, right? And then the absorber is just going to be like, oh, gee whiz, I'm really excited. And then it's going to release a bunch of gamma rays, but it's going to be in like random directions. So rather
Right.
than it just being like whooshu, it's instead going to be like bam, just in separate random directions instead of being just in one detecting place.
Okay. I like that. I absolutely love that explanation. Did that do it for everybody or no? It did it for Danielle. Did it for Ion and Audrey. Vivian? Okay. So let's say you have the source, the absorber, and the counting system, and then you remove the counter. Will the count rate go up or down, Vivian?
Did you say if you remove the counter?
I'm sorry, if you remove the absorber. I'm sorry, if you remove the absorber, will the count rate go up or down?
It'll go up
Right. Because?
because now it's all the rays are like streamlined towards the detector now.
I love it. Yes. Perfect. And if you put this guy in here, it basically scatters them in all directions, right? Now, in chemistry and in normal like stuff, the absorption is normally followed by radiationless decay. What do I mean by that, Wihan? Radiationless decay.
I think you mean by it's so the absorber is not going to be decayed, but then it will actually release the gamma ray.
Okay, that is exactly the opposite of what radiationless decay means. So radiationless decay means that the absorber is going to relax, but not emit a gamma ray. It's going to dump the energy into the heat bath.
Well, how would it do that?
It's a trick known only to molecules. No, so nuclei generally don't do that, right? Because they really don't interact with their environment in the same way that other things do. You know, that they're kind of isolated there. But for electronics of molecules and nanoparticles and and in vibrations and rotations, there's a lot of modes of motion, and there's a lot of ways for the energy to escape into the environment. But for nuclei, it's not that common. So if you're if I excite, if you're a molecule, let's say you're a simple molecule, you're like H2, right? Then I can excite you electronically. I can flip a spin or change a quantum number. And then when that quantum number comes back, it can put the energy into vibrational motion, right? That's a possibility, right? And then that vibrational motion can couple to the vibrations of other molecules in the bath, and then that can dissipate out, right? If it's in condensed matter, right? If it's in a liquid or a solid, or even a gas if it collides frequently. So that's actually the rule in condensed matter, is that excited states don't last. And they decay mostly non-radiatively. You know how,
So they would
Yeah.
just vibrate and disperse.
yes, exactly. Exactly. Ankita, have you seen a fluorescent thing?
I think so.
Like cadmium selenide?
yeah, I've seen
Yeah,
it.
you put ultraviolet light in and it puts out visible light, right?
Yeah.
Right? Am I right?
Yeah.
Okay, cool. So that's putting in an energetic photon. And these cadmium selenide nanoparticles are then dissipating a good fraction of that energy into the vibrational modes of the bath, of the solvent and nanoparticle, blah, 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 blah. Then they hold on to that last little bit, and when they decay from that last state, they emit a photon. But that photon is lower energy than the one that excited it. Right? That's the inevitable progression from excited state that back down to ground state. Rohan,
Yes.
where's your background?
Oh,
I miss the star, I miss the Death Star. I need the Death Star. Okay, he's gonna get the background, he'll come back. There it is. I love it. So, yeah, so in I was talking to Ankita, I think, right? About how when things are excited and they relax back down to the ground state, they generally, the amount you get of energy you get out as photons is less than the energy that you put in as photons. Because generally you put energy in as photons and then there's some relaxation modes, and some of the energy dissipates into rotational motion and vibrational motion and translational motion and you know, God knows what else is out there, right? Whatever modes are available, right? And then sometimes the last bit comes out as radiation, as light, right? And that the difference in energy between the input photon and the output photon has a name, and that name is Stokes, the Stokes shift, right? And that just pisses me off, because, I mean, what a simple ass thing to get your name on, a redshift. I mean, I could have predicted that. They could have called that the Roger shift. But no. Anyhow, so JJ Stokes got his name for that one. JJ Stokes, the Stokes shift. He's also named on the Stokes-Einstein equation. You guys probably got a Nobel Prize or two, but anyway, I digress. So back to the amazing diagram here. So this, for nuclei, the fact that absorption works to quantify the amount of absorber or whatever is a function of the fact that when there's a resonance absorption here, this is the same energy photon is given off that excites it, right? It's called a resonance absorption. That, these absorptions happen because the absorber will randomize the direction of the photons. And they generally have these things in lead tubes or something such that the off-axis photons are all lost in the lead, right? And lead is a good example of something that dissipates gamma rays, right? The gamma rays go into the lead and they scatter off the electrons. It's called Compton scattering. I don't know the mechanism, but it's one of these weird sort of semi-classical things. So now we talked a little bit about how there are a good number of nuclei that do this, but the cobalt iron electron capture system is a common one, right? And that the line width of the transitions that do this are super, super narrow. Let's see here. The line widths are super narrow. And they are broadened only by lifetime. So this is 100 nanoseconds. So how long is a nanosecond in light feet? Do any of you remember?
Wait, in light feet?
Light feet, right? So the answer is 1.
1 foot.
Yes, it's 1 foot. Good, Audrey. A nanosecond is 1 light foot. So this lifetime is about 100 light feet, right? 10 to the minus 987. So this is the average lifetime of an excited state of iron 57 is about 100 light feet, right? And that means that the line width in electron volts is equal to h bar divided by 100 nanoseconds, which is 10 to the minus 8 EV, right? So 10 to the minus 8 volts is an extremely small value. So you know how much a volt is, right? It's like a battery, right? Now take a thousandth of that, it's a millivolt. That's a very small value. Take a thousandth of that, it's a microvolt. That's a pitifully small value, almost hard to measure, Then go 100 times lower, and this is the line width. That is the range of energies over which these 100 keV, or I'm sorry, these 14 keV electrons. So 14,400 plus or minus 0.000000001 volts. That's what we're looking at here. So these resonances are extremely sharp. Does that make sense? Extremely sharp. So sharp, in fact, that if you have a system like this, where you can Doppler shift the source by moving it towards or away from the absorber, then you will see corresponding oscillations in the signal on a counter. Quick question. I would like you guys to predict for me, if you have a singlet source and in a singlet identical singlet absorber. So this is cobalt 57, and this is iron 57. So that the emitting species here are iron 57s, and these guys here are the same chemically identical iron 57s. I want you to predict for me what the proportional counter signal will be as a function of the velocity of the source between -5 and +5 millimeters per second. That's a lot of words to get there. I'm sorry. Maybe we should have a short breakout. Do you want to break out, or do you want to just keep going?
I prefer to keep going, but I'm fine with whatever.
Okay. All right. Who understands the question?
I got most of it.
Okay. So if you modulate the source, if you start with a source going away from the absorber at 5 millimeter per second, source is going to the left, and then it's going to the left slower, 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 slower. Then it's speeding up. Now it's going to the right, faster, 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 right? Then that corresponds to a Doppler shifting of the measurement, right? So at what point in that velocity modulation will the particle counter give a peak? And the answer in the units of millimeters per second. Okay. So, Vigo, do you know the answer?
Ah, ha, 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 ha.
Okay. That's not the answer.
Would it be 0?
Okay, why would it be 0?
Because that's when the resonance is created.
Why would it be created at 0 and not +5 millimeters per second?
Because there's no Doppler effect when it has no velocity.
Okay. What is the Doppler effect?
The buildup or kind of dispersion of the waves.
Yeah. Yeah. And what does the Doppler effect have on the energy of the gamma ray? So if the source is moving towards the absorber or towards the detector, is the gamma ray higher or lower energy from the absorber's perspective? Vigo.
Well, if the frequency is increasing, then wouldn't it be higher energy?
What do you think, Wihan?
I agree with that.
I agree with that too. What did we just do? We broke the conservation of energy. We broke it. Energy is not always conserved. Not always. Because what's different about these gamma rays except for the perception of their source velocity, right? Anyway, I'll leave it there. It's a little bit deep territory for me, right? But Vivian, when this guy is moving to the right towards the absorber and towards the particle counter, right? When it's moving to the right, why are they not absorbing? Why do the identical particles in the absorber from the source not absorb the radiation? That's a big mouthful, sorry.
I'm not really sure.
Okay. Who can explain it to Vivian? Ankita?
I'm not entirely sure, but would it be because it's more like streamlined? I don't know.
Okay. So when the source is moving towards the absorber, are the energy of the gamma rays being emitted in resonance with the energy that they can absorb it there? Yes or no, Jimin?
I guess yes.
Oh, okay. Raymond?
No, right, because they were like originally identical, and due to the Doppler shift, the energy is now higher because it's moving towards it.
Exactly right. Astra, if the source is now moving away from the absorber, are the emitted gamma rays in resonance with those in the absorber?
I don't think so.
I think that's right. Rohan, at what velocity is there a resonance between the gamma rays emitted by the source and those absorbed by the absorber?
Not sure.
Brian, do you know?
I have no idea.
Lucas?
What was the question again?
At what velocity are the gamma rays emitted by the source in resonance with those absorbed by the absorber? At what source absorber relative velocity?
At 0 millimeters per second, because then there's no Doppler shift going on.
Exactly right. Exactly right. Caleb, what if the absorber gamma rays were slightly higher energy than the emitted gamma rays?
Well, then it wouldn't work. You'd want to slide the gamma ray emitter like towards the absorber so that it's working again, right?
I think that is correct. Could you say it one more time, just so I can?
Sorry, I didn't phrase it very clear.
No, that's
basically,
okay.
so if the absorber is only compatible with higher energy rays, that means you need to make the rays higher energy, and one way to do that is to use the
Yes.
Doppler effect. And
Exactly right. Exactly right. This is just all basic resonance phenomena. The weird thing about it is that we're using a Doppler shift, a really tiny Doppler. This is 5 millimeters per second. That's 10 millimeters per second. You know, that's 1 centimeter per second. It's literally going this fast. You know, and so Sadhana, let's say that you're in front of me and I'm transmitting gamma rays to you, right? And we have the same gamma frequency, right? And I'm sending gamma rays to you and you're absorbing them. Right? And you're absorbing them. You know, whatever, right? But then for some reason, I'm moving towards you at 5 millimeters per second. Like that, right? And there's a tiny Doppler shift, right? Now, do you absorb those gamma rays or not when I'm Doppler shifting them?
You wouldn't, because the frequencies wouldn't be in resonance anymore.
Exactly right. Exactly right. Okay, so now that is the point here. And so when you want to examine the environment of a nucleus. Let's say an iron nucleus, right? And you want to say, you know, this nucleus is different from this nucleus because it's in an electric field, or it's in a magnetic field, or it has more or less 1s electron population. And I'm not sure about 2 or 3s, but definitely 1s, right? Then you can do this experiment where you look at the Doppler shift from a given source into that nucleus, right? And a lot of times you see these wild splitting patterns, and that's because of the strange phenomenon of alignment or opposition to local fields between spin active entities like electrons and nucleons and whatnot. And this is one you guys don't get, and you're never going to get it ever. And I'm going to say it till I'm blue in the face, and you're not going to get it. And I'll say it one more time, that when you put an electron in a magnetic field, it only has 2 possibilities. It will be aligned with or opposed to the applied field, period. There's no other possibility for it. And so that corresponds to one of these 2 peaks, right? One is red shifted and one is blue shifted. That's where the nucleon is aligned to the external magnetic field. That's opposed to the external magnetic field. Something like that, right? And I think that's pretty damn wild. And that is the basis of like all kinds of spectroscopy. Like nuclear magnetic resonance is one, or MRI, but we're a little bit more familiar with MRI, magnetic resonance imaging, which is basically taking pictures of the water in your body using a big old magnet and a radio frequency emitter, transmitter receiver couple, right? And even Mossbauer, which is like a completely different energy regime, right? From radio waves, which are, 0.001 electron volts, to these things, which are 15,000 electron volts. And the same sorts of physics underlie these weird splitting phenomena that you see. And nobody really understands it. The only person who got close was Paul Dirac. And nobody could understand Paul Dirac. But he was a pure mathematician. And when he saw that he couldn't make a quantum theory for electrons because the math didn't work out, he used different kind of numbers. He used tensors, he used matrices for the spin state of an electron. And not only did he get the spin of an electron out of it, he also got the anti-electron. And he was puzzled by the anti-electron, and he came up with some wild explanations. But the simplest one right now is that there is such a thing as an anti-electron. It's the same as an electron moving backwards in time, has all the same properties. And when anti-electrons and electrons meet, they annihilate into gamma ray pairs. But anyway, I digress a little bit here. But this weird phenomenon, right? It's where you can tune the energy of an extremely monochromatic gamma ray, such that it's in resonance with or out of resonance with an absorber. It gives you an analytical handle, and it also gives you an interesting phenomenon. Now, one of the first things that was done with that is called the Pound-Rebka experiment. This is their Wikipedia page. And they took this wild experiment that relies on, to describe it, you need all this quantum physics, right? And you can look at all the papers that back it up. They're all by Willis Lamb and Mossbauer himself and others, and they're all quantum physics, right? And they're all describing these energy states that are available and not, right? And then somebody realized, holy cow, this is so sensitive to changes in energy that we should be able to weigh a photon, right? Now, photons are massless, right? But they're not massless. I don't really get it either. I'm sorry. I don't really get it. But if you take this experiment and you turn it on its side and you place a source and a detector 20 meters apart of vertical displacement, then will the gamma rays emitted from this source have the same energy after they've traveled 22.6 meters up in a gravitational field? Yes or no? Who wants to vote on that? If the gamma rays emitted by the source after they've gone up in a gravitational field 22.6 meters up in a gravitational field, will they have the same energy as when they left the source?
No.
Okay. Ankita?
I'm not really sure.
All right. All right. So let me, Emma, why the fact that I'm asking this question implies what?
That there is an answer.
Yeah, there's an answer, right? And if the answer were 0, would I be asking the question?
Probably not.
Probably not, right? So, so if you fire a gamma photon up, will it lose, from the perspective of the detector, 22.6 meters up in the gravitational field, will it have more or less energy?
Less energy.
Wehan?
I don't know. Well, how does the magnetic field affect the photons?
The gravitational field.
Or right, the gravitational field.
Good question. Brian?
Does it lose energy?
Astra?
I think it would also lose energy.
Rohan?
I'm also thinking it would lose energy.
Sadhana?
I think it would lose energy.
Okay. It loses energy. Good. Excellent. So, and they proved it here, right? Now, why would something lose energy in a gravitational field? It has relativistic mass. It has relativistic momentum. P squared over C squared, something like that, I don't even know. but apparently this is equal to 1. And the velocity, oh God, I don't even know. Forget it. This is equal to 1. It has h in it, right? And there's this h affects the energy somehow, right? And I think it has to do with this v here. This v will be shifted relative to this h, but I'm not really sure. Okay, I didn't put that foil up. Just forget that foil. Oh, wait a minute. We're DLSing. My internet connection is kind of weird right now. So anyway, I'm just trying to kind of point out some of the weird sort of connections in science between these wild relativistic effects and these crazy quantum effects, and they can be, and they sort of meet in this case, right? That you basically need a relativistic correction to understand the quantum physics of nuclei when they're oriented in a gravitational field. So
the photons, if photons have no mass, why are they affected by gravity?
yeah, it's a very good question. So gravity affects space-time, right? And therein lies the rub, right? There's space and time. So there's one constant here, right? Which is the speed of light. But in a gravitational field, space is smaller. And so the space-time at a lower gravitational field point is different. So the wavelength is different. And so the frequency has to be different in order for C to be the same. So if the wavelength is higher, then the frequency has to be lower in order for C to be the same, in order for the speed of light to be the same in both contexts. And that's one way to understand this.
Okay.
You
So
know,
does that mean,
yeah, go ahead.
so does that mean that you can bend photons and light just with gravity, like the Earth, for instance?
Oh yeah, absolutely, absolutely, absolutely. Yeah, you know, it's like I don't really think you bend photons. I think you bend space-time, and the photons are just going in a straight line, and space-time bends, and so they bend. You know, it's like if you're going straight, but someone and there's a right turn coming up, but someone then, as you go into the turn, someone moves space-time, then you just keep going straight. But then from a different perspective, someone sees you going around a corner, you know? And I think that's kind of what's happening here, is that we see the photon lose energy, or we see the light path of a photon curve, but from the photon's perspective, it's just still going straight. And I'm sorry, I'm a little bit out of my depth here, so you know, ask hard questions, but I might not be able to answer them, or answers might be more infuriating than enlightening. So let's see here now. Let's would you guys like a why don't we, I'm thinking about, we can save this for tomorrow, or we can dive in now, but it's about the the melting of DNA duplexes and their detection using nanoparticles? Do you guys want to save that, or do you want to dive in right now? I'm totally fine either way. I'm totally fine either way. And you know, I'm sort of dancing in these waves, you know, and I just know enough to be dangerous. That's really what's going on here. Is I just know enough to be dangerous. And this is another interesting phenomenon, but this is all understandable within, you know, thermodynamics and chemistry, and there's nothing really weird about it. Raymond, it's all down to you. Do we move forward or do we take a break and pick it up tomorrow?
I'm fine with either too. So
Okay, who's going to opine here? Astra?
I mean, I'm feeling kind of tired, but I mean, I could probably continue if.
Oh, okay. I'm going to go with Astra. And I'll give you the idea of this experiment, and then we can talk about it in more detail tomorrow then. You guys are aware of, you guys know about the colorimetric tests with nanoparticles? Have you guys gone over that with Xiaowei?
Yeah.
Yeah, probably, yeah. And so you know that, like, if you have a set of probes, A and B, that are linked to nanoparticles, and you have a target in solution which comprises the sequence A prime, B prime. What that means is that A prime is the complement to A. Means whenever there's an adenine on A, there's a guanine on A prime. And whenever there's a thymine on A, there's a cytidine on A prime, right? And that in order, as you move out from the nanoparticle, then you move into this sequence A prime, and then A prime is connected to B prime, and then as you move from B prime to its end, you can couple to strand B going down there, such that a duplex will form between the nanoparticles and it will trigger the aggregation of these guys. And one of the beauties of this is that it works so darn well. There's some hormone that humans have in their pee that you can detect this way and know if someone's pregnant. It is crazy. It is crazy. You put these particles into like, you put them onto a strip, right? And you pee on the strip, and if they turn blue, then you're pregnant. You know, or you have this hormone, right, in your system, right? So it's a very consequential color. But underpinning this is some pretty wild chemistry, and the wild chemistry has to do with the duplexation thermodynamics, and something I'd like to chat with you guys about next time is the way that this duplexation depends on things like temperature and salt concentration and other phenomena like that. Okay, so we will reconvene next time, and I'll put this paper up if you want to take a gander at it. It's not required or anything. I'll just but I'll go ahead and put it onto I'll put it onto the Canvas page. I'll make a link to it in the calendar for tomorrow. All righty, guys. I'm so grateful to all of you for your attention. And let's see here. And I hope you've enjoyed this at least a little bit, huh? So I will see you all tomorrow. Cool.
Thank you.
Hi, thank you
righty,
so
thanks.
much.
Bye.
Thank you. Thank you, guys. Bye-bye.
Dr. Harrell,
Yes.
real quick, I was just wondering, this is for my own personal investment. Do you know anything about like chemistry internships for high schoolers?
I know that I can't do it anymore. I used to be able to do it, but they got all excited about the liability positions that we have. They got taken away, but I think it depends more on your age than your educational level. So if you're like 16, 17, maybe not. If you're going to be 18 soon, then we got a shot. And then and there's but so I don't know where you are on that spectrum, but
I'm gonna be 17 in October.
So I'll try to hear this out a little bit and I'll get back to you.
Okay.
All righty.
Yeah. Okay. Thank you very much, Dr. Terrell.
Awesome. Talk to you
Thank you.
soon. Bye-bye.